Vicky, you're still playing?
Oh. Oh, it's almost 3 a.m. Before I go to bed, I need to find a sand biome first.
Why don't you just use a map?
Okay, but biomes generate randomly, and there's 53 of them in the overworld, so if I have to keep walking and looking for...
Have you ever wondered how infinite biome generation works in the world-renowned, award-winning, hit 3D sandbox game Minecraft? Let's break it down for you. Minecraft, the hit sandbox game celebrated for its vast and varied landscapes, relies heavily on sophisticated computer algorithms to create its diverse biomes. Central to this process are noise and terrain generation techniques, which work in tandem to craft the immersive and intricate worlds available for a player to explore. Noise generation is a mathematical method used to create natural-looking randomness. In Minecraft, noise functions such as Perlin noise and simplex noise are utilized to produce the game's terrain. These noise functions generate pseudo-random values that influence the elevation, structure, and features of the landscape. World generation begins with the void below your feet. Then, white noise is used to add a layer of bedrock that has a completely random texture, and this happens throughout the whole map from y equals -64 to y equals -58. Next, as the world builds up, a general layer of deep slate is added from y equals -60 to y equals 0. After that, every biome is different, and stone is the main composition from y equals 0 to the biome's surface. Now, within these layers of deep slate and stone, other blocks are used to randomly replace them using RNG, which is how diorite, diamond ore, gravel, and small chunks of blocks are generated. After that, caves are carved using the same concept, except everything is replaced with air. Next, subsurface blocks are generated, such as dirt or sandstone in this scenario, usually covering no more than 20 blocks. And for the top 5 to 10 blocks are the surface blocks, where grass or sand or surface blocks for other biomes are generated. Structures and vegetation are added on top of that, such as cacti in this example. So, every time you see the chunks loading, this happens. Perlin noise, developed by Ken Perlin, is a gradient noise function that is renowned for its smooth, natural variations. It creates continuous, differentiable, undulating terrains that form the basis of Minecraft's mountains, ravines, and plains. Perlin noise helps ensure that terrain transitions are gradual and visually appealing. An improvement over Perlin noise, simplex noise offers lower computational complexity and less directional artifacts. It is particularly useful for creating detailed structures in Minecraft's terrain, like villages and strongholds. Terrain generation in Minecraft builds upon the foundation laid by noise functions. The game uses a combination of noise layers to define the height map, which determines the elevation of each x-z coordinate in the world. Here's how it works. Base terrain formation. The initial terrain is generated using primary noise functions, creating basic landscape of hills, valleys, and plains. Biome application. Different biomes are overlaid onto the base terrain. Each biome has unique characteristics, including specific vegetation, structures, and temperature ranges. Biomes are assigned based on various parameters, including temperature and humidity maps derived from additional noise functions. Feature placement. Trees, lakes, caves, and ravines are added to the terrain. Surface decoration. The final step involves adding surface decorations, such as grass, flowers, and other flora. You might be a little confused as to how exactly layers of these noise functions work, so we'll dive a little deeper. To reiterate, Perlin noise is an algorithm used to generate things like textures and terrain procedurally, without manual work by an artist or designer. Let's begin by examining how to use this algorithm. Perlin noise can operate in one or more dimensions, depending on the number of inputs it receives. The algorithm accepts a certain number of floating point parameters based on the dimension as its input. These inputs typically range from the values of -1 to +1. In a 2D space, the input will be two parameters, x and z, because in Minecraft, x and z axes create a flat plane, while y represents vertical height. To generate a texture, x and z would represent the coordinates of the pixels. Perlin noise stores and caches random values at the integer intervals on the coordinate grid with a random constant vector of length 1. The noise values at any arbitrary points are determined by the 4 nearest seed values on the grid. The math concept floor, expressed as floor with 2 parentheses, allows the nearest seed values to be found. For each of the 4 corners, we would take the dot product of the random seed vector with the vector from that corner to x, z. The values of each of the corners are clamped to a range close to -1, 1. They are denoted with UL, UR, LL, and LR. Next, you take a weighted average of all 4 corners. Perlin noise uses a weighted averaging function chosen such that values close to 0 and 1 are moved closer to 0 and 1, called the ease curve. Since the data values are continuous throughout the grid, we can interpolate along each axis and create 2 separate functions to merge into the ease curve. Then, we interpolate again to merge these 2 functions to find the total average and create the noise function. Therefore, to create a texture, we would iterate through each pixel, call the Perlin noise function each time, and then determine the color of each pixel accordingly. Also, fun fact, after every multiple of 256, the Perlin noise will wrap, aka repeat. This is also why the previous Minecraft build height was y equals 256. But that made us wonder, how else does computation show up in the games we play? Like the hugely popular, critically acclaimed, free-to-play, internet sensation battle royale game, Fortnite. Let's break it down for you. Again, this time with an expert.
My name is Jon Sourbeer. I work at Epic Games on Fortnite. I specifically do physics for Fortnite. I've worked on the main battle royale, and then recently worked on Lego Fortnite.
Jonathan is a physics gameplay programmer at Epic Games. As you can probably guess, he works with a lot of physics systems in Fortnite, an example being toys in Lego Fortnite like balloons and rocket thrusters. And, according to him, there's a lot of math involved in that kind of work.
It really depends on what problems you're trying to solve. On the physics toys, it's a lot of just translating real-world physics into computer physics, basically, which is an approximation. So all computer physics is just math designed to get as close as possible to real life at very low cost, because we have to do it very fast so that you can run and meet your frame goals.
Yeah.
A lot of video game math is dependent on vectors and vector geometry, geometrical functions, and then there is some further things involving calculus that usually is for calculations for physics themselves. So when you're working in a game world, you have, especially nowadays since we're in 3D, it also applies in 2D, but it's simpler math.
Yeah.
You have vector matrices, so linear algebra. You have geometry, so you have calculations for determining if things are colliding with one another. You have a topic called quaternions, which are designed... Oh, yeah.
Quaternions?
Oh, yeah.
She said quarter-ions?
Quaternions, yes. Oh, hey, you know what? You if you've never heard it before, you're not going to know how it's pronounced, so that's fine.
Quaternions, or quatern ions, as Kat calls them, are integral to representing rotations of 3D objects. Objects in space rotate along 3 axes: yaw, roll, and pitch. These are Euler angles that describe the orientation of an object. Yaw is for the vertical rotation, roll is for lateral, and pitch is for the forward and backward axes. Matrices are arrays of individual elements that are often used to store rotation information and transform vectors in 3D space. Each Euler angle is associated with a specific 3x3 rotation matrix that stores information about how the object rotates around a surrounding matrix. Then, to represent the overall 3D rotation of the object, the yaw, roll, and pitch matrices can be multiplied together to create one combined rotation matrix. Sometimes, gimbal lock occurs, which is when 2 of 3 gimbals become aligned and parallel, and 3 degrees of freedom, yaw, roll, and pitch, becomes 2, creating discontinuities or unpredictable behavior in the rotations. Essentially, information is lost, which is never good. This is where quaternions come into play. Rather than using the 3 yaw, roll, and pitch angles to store information, a rotation quaternion encodes the 3D rotation as a scalar and a vector. The scalar is comprised of 1 real number, while the vector is made up of 3 imaginary numbers. The scalar part W represents the angle of rotation, while the vector part R represents the axis of rotation. A 3D rotation by an angle theta about the unit axis vector AX, AY, AZ can be represented by this unit quaternion. Then, to rotate a vector around the quaternion, we use this equation, where v is the vector vx, vy, vz, and q to the power of -1 is the inverse of quaternion q. Quaternions are more compact than 3x3 rotation matrices and are represented in 4 dimensions, making them superior to matrices and Euler angles in 3D rotation. But if a game object exists in 3D, why and how is it represented in 4D?
A quaternion is a constrained 4-dimensional hypersphere.
Okay.
So what that means is if you think about constraints, there's a limit to things, right? A hypersphere is just, a 4D hypersphere is just a sphere, but it's in 4 dimensions, which is a little weird to think about. But to kind of get you there in terms of an example is if you think about the Earth, we're standing on the Earth, right? It's a sphere, right? But we can often represent when we move around as a map in 2D. And that's because we're always walking along the surface, right? So we're constrained to the surface of the Earth. So even though we're moving in 3D, we can represent it in 2D as we move around the Earth because it's constrained. It's the same basic principle for a quaternion, except it's in 4 dimensions, and we constrain it to 3 dimensions. So you're always moving in a 3-dimensional space, basically, in 4 dimensions. Quaternions is a field that usually what you want to do is you want to set it up correctly once and then never have to touch it again because you'll break everything if you do. And that's actually another thing is that there's a lot of things that if you're doing it correctly, you want to do it correctly once and then you never want to have to touch it. You'll set up, say, a math library, and that library will define how everything interacts physics-wise. And if you ever discover a bug in that, then it's a real problem because basically, let's say, since I work at Epic, I work on Unreal Engine. And that's used by, thousands of companies to basically do various things, various games, various, movies, automotive products, that type of thing, architecture. If we were to go in and change something in that library, all of those products would be affected because depending on how they're doing things or how they're using it, it might change their calculations. Suddenly a character in a game might jump differently, a car might turn differently, the way that they're building, if they're measuring, like if they're doing destruction or things like that, for engineering, might suddenly collapse differently and they get totally different results for their model. So there are plenty of things where it's like you need to know how to do it, you need to know how to do it right, and then you never want to touch it again.
You described a lot of things that obviously we haven't learned yet, so what level of education do you think that you would need to get a job like yours or use math like you do?
Well, I have a degree in physics and I have a degree in computer science and a minor in math. Those have all been pretty valuable for that. Part of it is just the drive and understanding the things. There are definitely people who just have a huge drive for math and get into it. Usually undergrad degree in physics or math and then computer science is kind of the minimum. There are plenty of people who also have PhDs who go into the field. It really depends on how extensive you really want to dive, especially into specific things. If you want to do generalized work, you might do several majors, or you might be broad. And if you want to do I really want to dive specifically into fluid physics or fluid dynamics, you might say pursue a PhD in something that allows you to really dive into that. But you don't have to.
I know you described some of the things you worked on and some of the math you used, but what's one very specific example of like a problem that you've encountered that you had to use like higher level math to solve?
I mean, just basic interactions in a 3D world require linear algebra. That is kind of the minimum if you want to get into the game space. There will be inevitably someone ask you, even if you want to do the basic programming, you will usually be asked a question involving linear algebra. So for example, there is matrix math, where you use matrices and vectors in order to calculate positions. And so in 3D, let's say you want to have a camera and follow a player, all that calculation needs to happen in real time. So you use 3D matrices. You'll create a camera matrix that is the representation of the camera and its focus and everything like that, and then you'll have a representation of the player and how it's interacting. So just those basic things are like something that are kind of even the fundamental level, and it's linear algebra. So
I guess as the last question, would you continue going into game development, or are you like, is that your fixed career, or are you thinking of trying out different things that are either math or computing related?
I think it depends. I mean, right now I'm enjoying what I'm doing at Epic. If I ever decide that there's something more exciting or I don't enjoy it anymore, I'll probably look for something else. The nice thing about being in the games industry in physics is that there's a lot of applications that overlap with robotics, drones, all sorts of, research applications, aerospace. So, when I was looking for a job before I went to Epic, I was talking with SpaceX. I worked at Amazon Prime Air. So there's a lot of different possibilities that you can go into. If you're not interested in games, and if you are interested in games, then there's a lot of demand for that, because there's a lot of value in order to be able to achieve something that is fast, efficient, and can keep people entertained at 60 frames a second.
Hopefully, this episode has helped you learn something new about your favorite video games. Thanks for watching, and don't forget to join us next time. Sony Pictures is made possible by viewers like you.